Hello everyone, it's July 31st. Okay, let's go right into it. Range sum query. Given an integer array, nums, handle multiple queries of the following types. Update the value of an element in nums. Calculate the sum of the elements of nums between indices left and right, inclusive. So that's segment tree, right? Implement the num array class. Okay, update index and val updates the value of nums index to eval. Int range sum, return the sum of elements of the nums between indices left and right, inclusive. Nums array, so we change 0 to 2. No, that's the sum range, 0 to 2. Now we update. 1 updated 2, and now we query again. Yeah, so basically, I think the only thing is they all say an update, right? So, but in BIT, it's not just update. It's what is in BIT? It's add. I think it's add value. So we just need the original value, right? Then we can do this update. Okay. Can you write BIT without looking at it? I don't think so. That's why I'm gonna just look at BIT. Yeah, come on. I can never write BIT all by yourself. So it's very important to learn how to write BIT by yourself. So how do you write BIT? Oh, I can't memorize. Bit I plus equal to delta I plus equal to I and minus I. So that's the update. Okay, so of course we're not gonna call it BIT. We're gonna use this. We're gonna use this thing. Okay, we're gonna initialize two things. All right, self.nums plus nums, and then self.bit. I call it BIT. Yeah, BIT equals to 0 times len nums plus 1. Okay. So we're going to update to a value. So we're going to say delta equals self.nums index minus value, and then self.nums index equals value. And then we're going to say I equals, I remember it has to be index plus 1 because it has to be 1 based. And we say while I, right? While I is smaller than len self.bit, say self.bit I plus equal to delta I plus equal to I and minus I. Right, let's see if it's right. I in position plus 1, yes. If I sum smaller equal to plus equal to, yes. That's it. That's the update. And sum range. So the sum range, I think I need to call it 2 times because say def query. Query, we have a position. Let's call it index. Okay, give you an int. So when I say I equals index plus 1, res equals 0. So while I res plus equal to self dot bit I minus equal to I and minus I. Is that right? Max R res is 0 while I plus equal to, yep, I've got to return res. So that's query. And then you're going to return self.query right minus query left. Oh, hold on. Including left and right. So shouldn't this be left minus 1? What if query is 0? Yeah, then it'll be 0. Let's try this. Doesn't seem to be right. Maybe it should be val minus this. That's the delta. Yeah, I think this is right. But the first one is wrong. Oh, I forgot to initialize. I see. All right, a couple of issues right there. So we do have to have a update as well. So def update self index and delta. Basically need this thing. Put it here, I equals this, smaller than, yep. So we have to update. So when you initialize, we should say for n in num self dot update I enumerate I, right? Update n. Once we're done, delta equals this, and then we do this, and then self dot update index delta. All right, and then this one has to be minus 1. Try this. Almost. Okay. So the initial is correct. We can actually do a few queries just to see if. So we're gonna do a few sum ranges. Let's do 2 more sum ranges. Let's say 1 to 2, 0 to 1. Should I do 1 to 1? You can see if its sum is the same. Method should be a string. Oh, I forgot. Okay, so the sum was correct. The problem is with the update. So the update, I update 1 to 2. So if I say, oh, come on, it's value minus, it's value minus. Yeah, this one should be right. There we go. There we go. BIT. This is one of those questions. If you know how to do it, it's not difficult. Yeah, this is one of those problems that if you know how, if you know if you know what data structure to use, it is not difficult. This one in particular requires segment tree, or better, a family tree, binary indexed tree. But that said, it is still, I'm still not proficient. Right? I am still not proficient at producing BIT from scratch. I think I'm getting a little bit better at it. Anyway, it's O log n, on for initialization, O log n for query, for update and query. We know that it's a BIT, it's one indexed, right? And then when you update whatever index comes in, you have a +1, and then you add the delta, and then you're gonna jump. And the jump is just I and minus I. Exactly what this means, I forgot. Okay. There's also something that, if you want to do interview, you better understand this I and minus I. And then in Python, minus I and minus I honestly don't know. You know what? Why don't we just take this opportunity? All we want to know is how so we can just say, let's pick a value. Let's pick 13, okay? It's binary 13. Minus 13. Actually, it's going to give you a minus value. Shoot. I need to turn this into... Actually, we can just 13 and minus 13. We can just take a look. 1. So, if think about what's 2's complement. We'll complement it. So the 0, 0, 1, 0. And then +1. So the 0, 0, 1, 1. Right? So we will add this, which is the I think it's the rightmost one. We'll find the rightmost one. Yeah. So we'll find the rightmost one, we'll add 1. And then if the rightmost one could jump a couple ways forward, then we just make those jump. Because the idea for this is we will update I think is you will always update the value. You will +1 or +1 0, +1 0 0, right? Or +1 0 0 0. So every time you jump, you do this like ×2 jump, and all those points will collect the sum for everything from the left all the way to there. So when you jump, when you query it, you go for whatever it is, then you jump forward to the previous point and jump forward. Yeah, I kind of understand. Still not 100%, but I kind of understand. So yeah, this is basically just BIT, segment tree. I think that will be the, yeah, naive is not going to work. SQRT decomposition. What the heck is SQRT decomposition? Yeah, straightforward, segment tree. Oh yeah, you have to calculate the total length of the tree, right? Yeah, whatever this shenanigan is. And like, nah, I'm not dealing with this. Yeah, BIT is so much better. Okay, so it's like another time encounter BIT. Right, this time I was able to get it. Did I use? I probably use both methods. But anyway, there's no point in go through them. We already know what's the optimal. This is the optimal one, the BIT. Such a good data structure. Yeah, sometimes you wonder how do these people figure it out? But still, if it ever happens again, now I have to redo this. I have to understand it anyway. Okay, that's BIT. Alright, how about we just come back to this and understand why this thing doesn't work, right? It works for these 3 cases, but doesn't work for the last case. So we have a loose bound on the left extending beyond the equals, but it has a tight bound on the right, which is, honestly, it's fine. We can print left, print right. Okay, this is the left. So for this will be 0, for this will be 1, for this will be 2, right? Makes sense. On the right is all at 4, okay? Actually try to print L sum, print I, L sum, and 0, 2, 2. Are you missing the L sum is 1? Actually, I think the left includes 3 is 3, 4 is 4. That is not right. Oh, 4 is by itself. Oh, I see what this one is. Oh, yeah. This is the index. So it's by itself. With the left. Makes sense. But on the right, we should have a big right sum. Minus 1 is 4, so this is 3. So P sum 2, 3 minus P sum 2 I times I minus left. Hold on. Yeah, we don't have to include I. So this is 10, right? We're here, so the right sum, the left sum is 0, right sum is 1, 2, 3, 4. That's it. 2 will be 2, 3, 4. Right, and then 1, 2, 3, 4. 2, 3, 4 is 9. Oh, 1, 2, 3, 4, I already counted. Yeah, because 2 cannot include the left, so 2, 3, 4. 3 will be is 3, 4. Huh. Which one I'm missing? You write it out. We have let's say based on 1. Oh, we're missing a lot. 1, 1, 2, 1, 2, 3, and then 1, 2, 3, 4. So based on 1, we're missing all these. So I have something here. And then the target. something here, right? So I say we ending this one, we get this, just so we can compute. And we say when ending here, but we're missing these things. Oh, I know which one we miss. Shoot. We are missing actually quite a lot. Well, for that, we have to, so basically for that we need to compute, let's say A1, let's say we have A1, 2, A3, okay? A1, A2, and A1, A2, A3. That's what we need to compute. And A1, A2, A3, A4. Alright, so just extends to A3. Oh, there's a lot more. Wow. So this doesn't work. I'll have to use his method. How? Why this one doesn't work? Should be everything ending in this, everything ending in this, everything ending in this. Okay. Which just means this times something. This times this times. So we just need to have all these sum times this. Okay. So again, we have back to this question, how do we calculate these? Let's say we have a 0, right? And 0, 2. Right. So we want this, this, right? So we use this thing to minus this. We have A0, we have to reduce A0. So it's the same thing, this, okay? Minus this. And minus this. Oof. So pay some 0. Oh, I copy some 3. Yeah, his method is better because I have to do another one. I kind of don't want to. I just need to understand this thing. Okay, so I have a little bit better understanding of how these things are. So what I want is sum here plus sum here. Okay, let's do this. Let's say we have here 1 on this side, 2, 3, 4, 5 on this side. Okay, so what we want is 2, 1, 2, 2, 2, 0, 1, 2. Right, 2, 1, 2, 0, 1, 2. I need the sum of this. And then on the other side, I need 3. Actually, 2, 3. Right? Then 2, 3 times 2. 2, 3, 4 times 2. 2, 3, 4, 5 times 2. So I need to put a sum of 2, 3, 2, 3, 4, and 2, 3, 4, 5. And the sum of these things into times 2. Right. And the sum on the left, when you do 2, oof, it's basically, I think it's 1, 2, 3, 0, 1, 2, 3, right? And then 1, 2, 3, 4, 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So we add it together, so that's 2, 3, 2, 3, 4, 2, 3, 4, 5 times 2, and at the same time 1 and 0, 1 times 3. Okay. And don't we have one more? We also need to have 2. 1, 2, 0, 1, 2. So on the left side. So these are just on the right side. And these on the left side. We can push this out. Hold on. What if I take 2 out? Say 2. 1, 2, 3, 0, 1, 2, 3. Okay, that's interesting. Then 2, 3, 4, 0, 1, 2, 3, 4, 0, 2, 3, 4. Then 2, 0, 1, 2, 3, 4, 5. And this way we have 3, 3, 4, 3, 4, 5. That's 3 times, 3, 4, 3 times, or 3 times. And on the left side we have 2, 1, 2, and then 0, 1, 2. 3 times as well. right? And at the end, that's just on right. On the left side, I have one more, so this is actually 4 times. Okay, now how do we handle this? What do we have? We have 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 2, 0, 0, 1, 0, 1, 2, 0, 1, 2, 3. 4. 0, 1, 2, 3, 4, 5. Okay. Let's say on the left level, we have 0, 1, 2. On the right level, we have this. And we want we have 3, 4, 5, 3, 4, and 3. Okay, so if we use this to minus this, we want so I say if I just 1 times 3. Okay. That means 0, 1, 2 times 3. This times 3, this also times 3. And hold on. It's r minus I. So it could be this, it might not be this. It could be just 3, 4, 5. So it's just this thing. Up to 5 minus up to 2. So we'll have this thing. And this thing. If this thing times 3, basically we have 0, 1, 2 times 3, and then 3, 3, 4, and 3, 4, 5 times 3, right? And we have this is on the left side. I still don't understand. So we're saying it has it times 4. unless I'm mistaken, right? I'll end it right here. I'll keep thinking. Adios.